All right. So this week, we're going to do lab, let me see. So lab 7. So click on modules and then scroll down and look for lab 7 at on the lab menu activities 7 magnetic field. So once you click on that, then this is what you have. So I'm going to bring out the activity here. All right, so Lab 7 is about magnetic field. And so the goal of this experiment is that you want to find the magnetic field strength, of various, materials. And for magnetic field, we know that a bar magnet can produce a magnetic field. So on the left, what you see here is that you have a bar magnet, and we know that a bar magnet usually comes with two poles, the north pole and the south pole. So if you follow the field line, which we use the capital B to indicate magnetic field. So when you look at the field line, you can see that it comes out of the north pole, and if you just follow that, and it's going to enter the south pole. Okay, and when you continue the line, you will see that it's coming out of north pole and coming into the south pole. So the magnetic field in this case is pointing upward. Okay, or if you use your thumb, and it's going to it's going to have a thumb that's pointing upward. Okay, so this is the directions of magnetic field, and you can see that it's just like following this curve. These are magnetic field lines. So in a way, it's very similar to a dipole, electric dipole, that you have a you have a positive charge, you have negative charge, and then the field line is for the electric field is from the coming out of the positive and going into the negative, if you remember. Okay, so this is the behavior of electric dipole. For magnetic dipole, because the north pole and south pole, they always come together, so we call that magnetic dipole, and it's always coming out of the north pole and enter into the south pole. So the magnetic field is in this direction for magnetic field. Now, at the same time, when we look at the diagram on the right, you can see that this is the wire, this is the tightly wound wire, and we have the current that's going into the wires. So when you have a current that's going into the wires, let's say, in this case, that the directions of the current, you use your right hand, so the fingers, you curve your fingers along the along the directions of the current. In this case, it is counterclockwise. So in other words, a current flowing is going in this direction. So this is the current going in this direction. So it's counterclockwise direction. And your thumb will give you the directions of magnetic field. So in this case, so this arrangement is exactly the same arrangement like this. So we have the north pole, because when you curve your fingers around the around this, so this is your finger that's curved around this. So your finger basically making a counterclockwise, is in the counterclockwise directions. Then your thumb indicate the directions of the magnetic field, and the magnetic field is pointing upward. So because it's pointing upwards, we know that this is the north pole and this is south pole. So this basically tells you that, just based on this diagram, you cannot tell which one is a bar magnet and which one is a current carrying wire. And so they both produce a magnetic field, okay? So this is naturally in nature that you have a bar magnet that will produce a magnetic field. Now, and in this case, when you have a current carrying wire, when you turn on the power supplies, when the current is flowing through the wires, it's going to produce a magnetic field. Okay, inside, inside this, inside this current. I wouldn't say inside. I mean, so this is like, let's say, a solenoid. So inside is actually hollow, and then so it's going to produce a magnetic field in the space, inside the space of the current carrying wire. Okay, and so that tells you. So the question is, what is the magnitude of that magnetic field produced by this current carrying wire? And the ampere, it actually deduced that if you integrate the magnetic field along the path, and that the result is going to be proportional to the current in the wire. So in other words, mathematically, this is the equation that describes that behavior. You integrate the magnetic field along the current carrying wire, and then after you sum up the sum up all the contribution, it's going to be equal to a constant times the current in the wire. And that constant mu naught is called permittivity constant, and this has a magnitude of 4 pi times 10 to the negative 7. Okay, and so this is expression, the line integral of the magnetic field, and that's going to be equal to mu naught times I. So for solenoid, when we use a solenoid, that kind of configuration, and with that kind of geometry, the geometry of the solenoid, you will be able to deduce that the magnetic field will have this expression. Okay, so the magnetic field is equal to the constant mu naught, and then times the n. N is the number is the number turns per unit length, and then times the current in the wire. So what is mu naught? Mu naught is the number turns. So that's a solenoid. You have this number turns, and then and the length is this length. Okay. So then you'll be able to deduce the number turns per unit length, and then that's going to give you the magnetic field. And the unit for magnetic field comes with the SI unit for magnetic field is Tesla. Okay, this is the SI unit, Tesla, and Tesla is a pretty big number. Usually you hear how many Gauss. So Gauss and Tesla are both the units for magnetic field. Tesla is the SI unit, and Gauss is is the one that is one over 10,000 of the Tesla. So 1 Tesla is equal to 10 to the 4th Gauss. So we can see that Tesla is a pretty big is pretty big. Okay, so this. So in this experiment, you're given four different material. You're given 4 different scenarios, and you want to find the magnetic field. One is the a bar magnet. So you want to find the magnetic field of the South Pole, and coming from the South Pole and coming from the North Pole. You're given an iron bar, which which itself has a very weak magnetic field, and the solenoid, once you turn on the power, it's going to have a current in the solenoid, so it's going to produce a magnetic field. You want to map out the magnetic field inside the solenoid, and then we're going to another scenario is that you place the iron bar close to the bar magnet so that the iron bar becomes weakly magnetized due to the that's induced by the bar magnet, and want to find the magnetic field strength of that induced iron bar. Okay, so there is what we call the zero Gauss chamber, which is used to zero the sensor, to calibrate the sensor. And the sensor is the magnetic field sensor that we use. And so it comes with the 2 different settings, radial and axial. And so in this experiment, we're going to use the axial, and the amplification is set at, we're going to set at 1. Okay. And so this is a sensor that looks like this, and there's a tap button. Usually, this is when you press the button when you insert the sensor. So this is the tip of the sensor. When you insert the sensor into the zero Gauss chamber, you want to press that button to zero sensor. To have it calibrated, you only need to zero the sensor once. Okay, so once you have the sensor zeroed, and you would so the experiment for the bar magnet is that you have a bar magnet placed on the meter stick, and this is the magnetic field sensor. So you want to, and the separation between them is X. We call that X. So you want to, move one of the either the bar magnet or the magnetic field sensor, creating 1 centimeter spacing each time, and measure the and then use the sensor to measure the field strength. And then you're going to increase the separation 1 centimeters at a time, and then until you get enough data points to map out the magnetic field lines produced by the bar magnet. And then the white dots here indicate the North Pole. So once you complete the taking the data from the North Pole, then flip the bar magnet, zero the sensor, and then redo the experiment again. So you're going to have another set of data from the South Pole. And so you would do that. You would do that for the iron bar as well. Okay, it's exactly same procedure. And then for the induced iron bar, you just place the iron bar and the bar magnet close to each other, have about like 0.5 centimeters, and then for about 20 seconds, and then so the iron bar will be weakly magnetized, and then you just remove the bar magnet, and then place the induced iron bar on the meter stick, and repeat the experiment again, and you flip it, and then so you have the South Pole and the North Pole. So just by when you have the North Pole right here, so this indicates the North Pole. So you would expect that. So you want to find out, what is the polarity of this induced iron bar? Is it so on this side? Is it the North Pole, or is this the South Pole? So this indicate, and capital M indicate magnetized. So this is, so what is MM? Is it a North Pole, or is it a South Pole? So based on the data, you should be able to deduce that. Now for the solenoid, you would connect your circuit like this. So you have the power supply, and let me see what is the power that we output. So you're going to output a 10 volt. So you output a 10 volts to the circuit. So, and this is your ammeter. So you're going to use the meters to measure the current in the circuit, because remember, it is the current that produces current in a wire that produces magnetic field. And by Ampere's law, magnetic field is proportional to current. So you need a measurement of current. So you have the, so this is the positive power supply connected to the positive end of the ammeter, and the negative end of the ammeter connected to this, and then this one, and then it goes through here, and then comes back to this ground. So this is ground, so this is more negative. So this is more negative, and this is more positive, okay? So you have the first arrangement. So you have that the positive end on this side, and then you're going to insert your magnetic field sensor all the way inside the solenoid. So the starting position X is 0. Between them, separation between them is 0, and you want to take the measurement, and you're going to give a 1 centimeter spacing and take the measurement each time. And then once you're done, once you come taking enough data points, and then you flip it, you flip, so then the second round is that you have the negative here, you have the positive there, and you take another set of measurements. Okay, so that will be regarding how you take the data, and then what you're going to do is that you want to plot your graphs. So you would have, let's say the data. So let's look at the table. So the distance is from the zero separation all the way to 15 centimeters apart between the sensor and the objects. And so the North Pole indicate that the end here indicate the North Pole is facing the sensor. So you have a set of 15 data points. And the south end is, so for this one, it is the south end that's facing the sensor. So you have the positive here. This is where the positive end is facing the sensor. Negative indicate is facing the sensor. Okay. So this is for this table, you have the bob magnet, you have a solenoid, and the current value will be given, and the number 10, you need to figure out, and you can do the calculations from Ampere's law measurement. I'll tell you how to do the measurements, and then you can compare the error. And the others, the second page, so this one is the iron bar, the first and the second end, and the induced iron bar, you have the data, okay, and then you can do the plot. So ideally, I would like you to do the plot for each. So altogether, there are four different material objects. So let's say for bob magnet, you would plot the magnetic field as a function of position, okay, and then you can see what kind of. So ideally, I would like you to have the both positive, the both north pole and south pole on one plot. So altogether, you would generate four figures. Each figure has two lines. One indicate for the North Pole, and one is for the South Pole. Now for the solenoid, we mentioned that the solenoid would have a measurements, and then you're going to compare your solenoid measurement to the theoretical measurement. So for solenoid, you will plot B, B versus X, and what you're going to find is that the solenoid as a function position, so this is a zero line here, okay? You'll find that it actually look like this. Okay, one's for, so this one is for the north, and this is for the positive, and this is from the negative, from the data. So basically, when you look at this diagram, you will notice that the magnetic field inside the solenoid is actually relative constant. So how do you figure out the measurement of magnetic field from solenoid that you're going to use to compare to the theoretical value? Here's what you want to do. I think the first 3 or 4 data points, I think it's either 3 or 4. They are relative constant, find the average. Okay, so you have one average here, and then the negative will be the same, 3 or 4 points, find another average. Okay, so you have one average from the positive, one average from the negative. Then you're going to do the further average. So your measurement BM is equal to the sum of the positive plus the negative. Now you don't want to directly add them together, because when you directly add them together, you're going to get a value that's very similar, that's close to 0. What you want to do is that add this to you want to add the absolute value of this to that, okay, and then take and then divide it by 2. Then that will be the average value of the measurements. Okay, so in other words, this is the positive value from the average, and this is the average from this negative value. So you want to turn this negative value, use the absolute value of this negative value and add it to that, and then divide it by 2. Then that will be your BM, and that BM is where you enter it here. Okay, that is your BM there. Okay, all right. So how do we find out the number turns? So in the analysis, it tells you that, let me see, in step 10, it says that the number turns is 2090 and 2920 turns, and the solenoid has a length of 11 centimeters. So you want to, based on this information, you should calculate the number turns per meters, okay, and per length, and everything has to be in SI units. So the centimeter has to be converted to meters. So that's basically what you want to do. Altogether, there are 8 data sets, and you want to plot them and making it into 4 figures, okay, and then 1 figure for each objects. And let me see what else. Let me see. So I think that's basically what you want to do for this experiment. And there are some questions in analysis. So you want to make sure that you answer those questions, and also remember to write figure captions immediately below the figures that you have. Okay, and so let me bring up the the data. So the data you're given looks like this. Okay, so you have the distance of the data you have is an Excel file. So you have the this. So BNC is actually for the bar magnet. So you have, let me see. Yeah, it is bar magnet. So you want to plot them in one figure. And and the D and E column, these are for the iron bar. And F and G are the induced iron bar, and H and I are for the solenoid, and the positive is actually in column I, and negative is in column H. The current measured is 128.5 milliamp. So you need to calculate. The number of turns per length or per meters. And the theoretical magnetic field can be calculated using the Ampere's equation, that's mu naught Ni. And experimental value, as I mentioned, if you look at the first, in fact, I think in this case, the first three data points are relatively close to each other. So you can just use the first three data points and use the average and then average again to find the experimental value of the magnetic field, and then compare to the theoretical to get your percent error. Okay, so that's basically what you want to do. The data analysis, I mean, although it seems there's a lot of data, but basically you don't have a lot of calculation to do. You just need to do the plotting. Okay, alrighty.